Okay, let's start this lecture by diving right into ethers. Just as you can make amines by putting alkane chains onto ammonia, you can make first alcohols by putting an alkane chain on one side of an oxygen, and then by putting an alkane chain on the other side of oxygen, you make yourself an ether. So, ethers are similar to alcohols, but the second hydrogen has been replaced by another alkane chain. So, let's zoom in on our ether. The oxygen is, of course, still more electronegative than carbon, so you're going to get this polarity. The oxygen is going to have a partial negative charge. The carbons are going to have partial positive charges. The molecule will have this region of polarity, so it will be capable, depending on the size of the chains, of dissolving in water. If the chains get too large, then they can't dissolve. Their non-polarity will overwhelm the polarity of this ether. They're less polar and less reactive than alcohol, and they're a common organic solvent. When it comes to interacting with water and with bases and so on, a lot of the changed activity comes from the oxygen here. For example, dissolving in water, it can receive hydrogen bonds, but it cannot initiate hydrogen bonds. That is to say, it's missing that hydrogen. So, where an alcohol can both give and receive hydrogen bonds, and thus it interacts very strongly with water and with acids and bases and so on. The ether lacks that hydrogen, so it only has half the hydrogen bonding equation. So that sort of thing shows up a lot in the reactivity of ethers. They're just less reactive because they lack that proton. They have that carbon chain on the other side instead of the hydrogen. When it comes to naming, ethers do not have priority, ever. So they're like halogens in that respect. When you see an ether, it's always going to be a side chain. The main chain, whichever one has priority, either because it has a suffix group or because it's longer, is going to be an alkane as normal. And the side chain is going to include the oxygen, and it will be named an alkoxy. So if there's only one carbon, it'll be a methoxy, 2 carbons, ethoxy, and so on. Ethers, they don't seem to show up much in nature, but they're pretty popular in industry and in medicine. They're big in plastics. They're also important as solvents. They're less reactive than alcohols. They're just not very reactive in general. And they're good at interacting with water in a non-reactive way. So they're very popular as solvents. They've also been popular as anesthetics in the past. The common name ether, given to diethyl ether, was for a very popular anesthetic once upon a time. But other than that, there's probably there are definitely a whole lot of uses. You're less likely to see them, though. And next we have our aldehydes and ketones. They're grouped together because they share a common functional group, the carbonyl. Here we have the aldehyde on top and the ketone on the bottom. You'll notice that the difference between them is the position of the carbonyl, that double-bonded oxygen. For an aldehyde, it's terminal, it's at the end of the chain. For a ketone, it's somewhere in the middle of the chain. And that's really the big difference between them. They do have differences in reactivity, though, which is why they're grouped separately. Early researchers, lacking the ability to, actually study molecules directly by looking at them with incredibly powerful microscopes, instead had to characterize them by the way they reacted. They found that these were similar, but not exactly the same. That right there is the carbonyl. That's the double-bonded oxygen. That's the functional group we are talking about. And that right there is what's known as the carbonyl carbon. thanks to the strong electronegativity of the oxygen. It gives the characteristic, partial negative, partial positive charges. And that is what determines a lot of the reactivity of your aldehydes and your ketones. Now, when it comes to naming these bad boys, if they don't have priority, then they're named the same. Okay, that is to say that the carbonyl is called an oxo group, or an oxo side chain. But when they do have priority, then the aldehyde turns it into an alkanal, AL ending, and the ketone turns it into an alkanone, an ONE ending. Aldehydes and ketones are very, very important in nature, unlike the ethers, which are far less common. For example, every sugar ends in either an aldehyde or a ketone. For example, here's glucose. It's an aldehyde, and it's chain form. In the ring form, the carbonyl carbon will react with the carbon at the other end of the chain to produce the ring. Excuse me. No, it's the carbonyl oxygen actually reacts to make the ring form. Anyway, it forms a cyclical ether. But you also get aldehydes and ketones in what are known as ketone bodies. That's these three molecules right here. Formaldehyde, propanone, and acetoacetone, and this third one, whose name I can't recall off the top of my head. But they are formed during, they're made by the liver, actually, out of some of the things that would normally be entered into the metabolic cycle. So they show up far more often in fasting or starvation, actually, or prolonged exercise, or type 1 diabetes, or prolonged alcoholism. You'll get these ketone bodies in larger numbers in the bloodstream. All of these have in common that the body is desperate for energy. It's desperate for food, for metabolism. There's no glucose available to put into the citric acid cycle, into the metabolic cycle. So instead, it starts breaking down other things, and then creating these ketone bodies, because these ketone bodies can be entered into the metabolic cycle at other points in order to get energy. So that means that people who fast, whether they're dieting, extreme dieting, or for religious reasons, or people who are actually starving to death, or people who have undergone prolonged exercise. By prolonged, we're talking hours of exercise, not just a good long workout. Type 1 diabetes, because the body, the insulin is being ignored or not produced. The body just can't get sugar into the cells. And alcoholism, we're talking an alcoholic binge with not enough food. So they're always starved for sugar in that way. And now, before we take off on the next stop on our little tour, let's talk about some common names. Remember, systematic names, are always preferred, but some things have common names that are likely to never ever go away just because they've been around for so long, and they are names for things that we use all the time. We've already covered some of these with the benzene groups and so on. Let's talk about some of these smaller molecules. First up, we have this pretty little ditty. This should be ethanal. It is, in fact, acetaldehyde. It's an ethane with the carbonyl on it, so it's always going to be an aldehyde. There's no middle of the chain on that one. And notice that acet, the ACET, shows up a lot when you have this 2-carbon thing, especially when it has a carbonyl. It shows up pretty frequently. So whenever you see acet, it's like an acetic acid or other things, you'll know that you're dealing with a 2-carbon chain. That's why it shows up in those ketone bodies that we talked about earlier. acetoacetate and so on, because in order to enter things into the metabolic cycle, the citric acid cycle, your body breaks them up into 2 carbon chunks. Yeah. Anywho, next up, looking down on the lower left, what should be methanal is in fact formaldehyde. Just a carbonyl with 2 hydrogens on it, basically. And over on the right, they broke away from any pretense of systematic naming. It's not propan-2-one, it's not even propanone, it's acetone. Something you may remember or may be familiar with because it's a nail polish remover. So it's a very common household product. It's also very, very common in chemistry laboratories. It's a good organic solvent. They also use it to clean things. It shows up all the time. Chemists basically, bathe in this stuff. Not literally. But those are some of the common names that are out there. We'll encounter a few more. I just wanted to throw those at you. But for now, let's go ahead and get away from aldehydes and ketones and move on. Unfortunately, there's no way for me to cram the next side chain, the carboxylic acids, in here in just 4 minutes. I've already recorded it. I'll be putting it into the next lecture, but I went on for a while. 12 minutes, in fact, uninterrupted. So we'll be cutting it off here a few minutes early.